Hello. In this episode, we'll use reinforcement learning, deep Q network, to price options. First, let me give you a quick overview on what we're gonna do. So just a quick reminder of stock options. It's like reinforcement learning, and in the option context, so we have a reinforcement learning agent, our program. It watches the state, which is the current stock price, and then it chooses an action. And in this case, whether exercise an option or not. Okay, so if you don't exercise an option, you just keep going to the next stock price and watching the state. But if you do choose to exercise, then we stop the game and you get an reward, isn't it? The option payoff. It's a terminal day payoff. So the hockey stick plot will be paid, isn't it? You may initially the agent, when it's on that train, you may just exercise it when the option value, the stock price is below the exercise price, and you actually lose money. But hopefully, as it gets smarter, it will only exercise the option when it's above the exercise price. The stock price is above the exercise price, and hopefully at an optimal point. So let's see how that works out. Okay. Conceptually, we'll use deep Q network, which uses a neural network to have the Q values. But essentially, you have two Q value functions, isn't it? One Q value when you keep going, and one when you exercise and actually stop the option and get the reward for it, isn't it? And conceptually, if you look at all dollar value at a state, okay, for each stock price value, which is a state, you have a Q value for whether you exercise or not and get a value for it, and you choose the action that is the largest. Conceptually, that is what we do, but we'll use a neural network to fit this value function here instead of having discrete tabularized prices, because there are so many stock prices. Okay, so this is at the end of the day what we'll see. You can use a Q table method, which it works until we exercise, and after we exercise, we don't care really. So it's around here. But you can see that this terminal day payoff when we exercise, which is actually known, and the blue dotted line is the continuation value. And so before the exercise, how does the value look like? And it actually resembles what we postulated hypothetically, theoretically, in an option review class, that it lies above this terminal day payoff. With neural network, we recover similar examples like this. Okay, so let's see how that works in actual Python program. So first we import libraries. Okay. So these are mostly the Keras TensorFlow will be what we are using. Okay. Okay. And then set the key parameters. So there's only one input because it's the current stock price that we'll be using. Okay, so we'll observe the current stock price and then go through middle layers or hidden layers. And then the output dimension is the Q value. I only have one Q value. Why is that? Okay, so you could have two values, Q values, like continue and exercise. But the Q value for exercising the option is actually known. It is the hockey stick plot. The hockey stick plot, when you exercise an option, what money will you get, what reward you will get, is actually known. You don't need to neural network compute it. You know it. So you can just tabulate or have a formula and pull it out, okay, without having to waste computational resources. All right. So we only need a neural network that predicts the Q value for continuation, okay, given that the exercise Q value is known. Let's have a Q network. Now we have three middle layers. And again, I don't need batch normalization or dropout. You're welcome to use it. But I do need the dense layer and the key value. And then it's DQ in and DQ out, DQ in and DQ out, like the functional API method. We'll use mean square error and Adam optimizer. Okay, that was easy. So choose the action. So here we'll get the Q0 and Q1. Okay. So continue is A0, stop is A1. Okay. So if Q0 is larger, then continue. If Q1 is larger, then stop, isn't it? And we do the epsilon greedy exploration, meaning we choose the non-Q maximizing action sometimes, just to get out of the local optimum traps. And then we need some environment. For the environment, we need to simulate the stock price. So let's just simulate a geometric Brownian motion, which is oftentimes, I just copied from a book, but you are welcome to try other methods. But this is like a way to implement geometric Brownian motion. If you type the WIP in Wikipedia, you will find the formula. That's it. So get the Q1. When you stop, again, we do know the Q value when we stop. It's the terminal option value. And for a call option, which option type, we'll just use one option type, call option. So let's just have option type 1. I'll always use this one. Which the Q value is the stock price minus strike price. Okay. Option is 1, isn't it? And the strike price is normalized to 1. So we are playing as relative to the stock price is a relative stock price relative to strike price 1. Okay. All right. If the Q value is negative, then it's 0, meaning it's either stock price S minus K. If S minus K is negative, then it's 0. Okay. So that's the option payoff when we exercise the option. The immediate reward is that, well, of course, if you have a call option, if you exercise it, then you get that reward S minus K, okay, or 0. If you don't exercise, of course, the reward is just 0. You just keep going. The next state is, well, you get the geometric Brownian motion, put the current stock price, get the geometric Brownian motion, and get the next stock price. So very simple. So the environment is basically, you have a current stock price and a chosen action. Put in the next state. So for a given state and stock price, you get the next stock price, you get the reward, and whether you stop the game or not. Okay, and that's on the state and future stock price, reward, and the indicator where you ended the stock price game or not is there. And then comes the usual deep Q network. You build a deep Q network. The learning parameter 1%, time discount 99, exploration 30%. Total number of possible actions are 2, and option type is a call option. So we'll just use 1. Okay, so the simulation of the deep Q network is pretty much similar. So we'll have 10,000 episodes and we keep playing and playing and exercising the option. For one episode, for one run of stock, we'll have 252 trading days. That is the number of trading days in a year. Multiply by 10. So we play the game as long as 10 years if we choose not to exercise and keep waiting. We almost certainly will exercise the option before then, but so randomly choose an initial state here as 0. So that gives the starting value. Okay. And action first is continue. So the first action will always choose continue and then keep doing. So we pick the Q value for Q0, continue, and Q1, stop, and choose an action that is Q maximizing action, but with 30% chance, there is, we choose the other action. So once we have the state and action, we can get the option environment, next stock price reward, and the indicator we end the game or not. After that, we do the Q learning, which is get the future, the next period, Q0 and Q1 value, and get the maximum of it. Okay, and then the target is mostly copying the Q1 from the previous round, but the S value will be the whole value, and we have a target, which is basically the R plus gamma max Q. So we do have that target. Okay, so we compare against that. So since we have only one state here, we can just compare it against this, isn't it? It's a special case. And then update the time, update the stock, and keep going and keep playing the game for a long, long time, isn't it? So it will do run it. It will take for a while because we are running it 10 years of 10,000 episodes. It takes quite a while to run it. So let's come back when it's done running. Okay, it still keeps running. So I actually have run it before. So let me just use that portion here. So the Q values are, let's see how it's being trained. Okay, so after being trained, we want to have a grid of Q values and how it looks like. So for how the stock prices, I think we scaled, normalized the strike price to be. So it's the stock price divided by strike price, if you think about it, to 1. And then we plot up to 2.5 of the stock values, normalized stock values. So the Q values can be computed accordingly using the DQN is already trained. So you just put the stock price in and it will predict the continuation value of it. The exercised case is the hockey stick, which we already know. So the orange line is when we start the option and exercise it, that's the hockey stick. What you can see is that the continuation value does actually show here. And when it crosses here, it's basically when it's an optimal time to exercise the option. So you don't want to, of course, exercise the option when the option stock price is below the strike price, so you lose money out of it. But even here, when it's just a small gain, you could have waited a little bit longer and exercise it at a higher price and get more money out of it, isn't it? So you might want to wait until the stock price rises sufficiently high. But do you want to wait it? How long do you want to wait it? Do you want to wait forever and get even higher stock price? And the answer is no. Someone said that, in the long run, we are all dead. So we are not going to wait forever. And there was a time discount factor, 99%. So with the compromise of I'm reasonably patient, but not superly patient. So I will wait only up to a certain amount when the stock price is up to a certain amount, which is here, isn't it? So this is the optimal trade-off between waiting for higher stock price to end and exercise at higher price versus I just get the money here, isn't it? So this is about showing how to implement real option pricing and optimal timing of it using reinforcement learning, specifically the deep Q network method. Thank you for watching this episode.